Welcome to our tutorial on digital electronics, and today we're gonna discuss about the adders. Okay, so the adders, as you can see here, they represent certain electronic circuits which add binary numbers. Okay, so what would be obtained by adding binary numbers? Pretty obvious question. Okay, so by adding binary numbers, the adders represent the simplest form of data processing. Okay, and in our modern electronic world, none of the applications, or rather any sophisticated application, requires the use of processors. So in the core of the processor's ALU, that's the arithmetic logic unit, the adders form the basic building blocks. And thanks to the adders, today you're gonna, you can just use mobile phones, your calculator, your computer. All of their processing capability is just due to the advent of this adder. Okay, so without much further waste of time, I would move on to the first type of adder that was created. That's the half adder. Okay, so in this half adder, what we find is that the half adder is a piece of electronic circuitry, or rather a digital circuit, which is just capable of adding up to 2 binary bits. Okay, it can add only up to 2 bits. Okay, so if we have, let's say, for example, this square block that I've shown over here represents a half adder. Okay, so in this case, let's just consider these 2 lines represent the input lines of the half adder, and we have 2 input bits, that's the A and B. Okay, so now the half adder would contain 2 output lines as well. Okay, one would be the sum from the half adder, which is obviously the result of the addition of the 2 bits, that's the A and B, and we'll have the carry. Okay, so why is there a carry line? Okay, let me just show you by means of an example. Okay, so consider that we're adding binary numbers. Let's say we're adding a 1 and a 0. So in this case, the addition is pretty simple, and we would obtain a single bit result, that's 1. Okay, what if we have a situation where both the bits being added are 1s? In this case, we wouldn't obtain a single bit result. The result obtained in this case would be a 2-bit result, and that is by the basic laws of digital arithmetic. 1 and 1 make 10 in case of digital arithmetic. So here we can see that we obtain a 2-bit result by the addition of the 2 input bits. So here, in case of this result, the units digit, that is, I'm just giving you, or rather just trying to relate this to the conventional arithmetic that we have learned in while in lower classes. So this units digit over here, that's the 0, represents the sum of the the addition, and here this tens digit, that's the 1 over here, represents the carry. Okay, so if we are using a half adder, okay, and both our inputs at the half adder are 1s, okay, then we would obtain a sum that would look somewhat like this. All right, so that is pretty much explained. So now if we just try and bring this out by means of a truth table, then I think it would be better. So here is our input bits, that's the A and B, and there's our carry and sum. So if our input bits, I'm just laying down the combinations, or rather the various types of combinations of the inputs that are possible, okay, with 2 bits of binary, with only 2 bits. So that's it. So now, due to this type of input combination, the sum and the carry would be as follows. So when both the bits are 0s, both the sum and the carry are 0. It's quite simple and straight. And when one of the bits is 0 and 1, we have the sum as 1, which is obviously a single bit result, and the carry bit remains 0 as well. Now in the case where both the bits are 1, so in that case what we see is that the sum bit becomes 0, as shown over here. As you all can see, in this situation, the sum bit becomes 0, as 1 plus 1 makes 10 in terms of digital arithmetic. So the sum bit becomes 0 and the carry bit becomes 1. So that's the truth table as obtained for in case of a half adder. So based on the pattern of output generated in the truth table of a half adder, we can construct its circuit by means of using just two very simple logic gates. We would require an XOR gate, okay, that would produce the sum of the half adder circuit. Okay, the inputs to the XOR gate represent the input binary bits as A and B, and along with it we would require another gate, that's the AND gate, for producing the carry of the half adder. So in this case what we see is that the sum given by this XOR gate, okay, if we just try to formulate the mathematical expressions in this case, it would be nothing more than A XOR B. That's the mathematical relationship for this sum obtained as in case of a half adder. And for the carry of a half adder, the mathematical relationship stands something like this. That's carry equal to AB. Okay, so if you'll just try and use these mathematical relationships, and for each of the input combinations over here, you would obtain the same sort of sum and carry bit results as previously, or rather that I've just showed you here in this truth table. Okay, so that was all that I had to say for half adders. But wait a moment, I'm just missing something out. Okay, what I just forgot to tell you is that the half adder has a problem. And what's that problem? Okay, I didn't miss it. It can add only up to 2 bits. That's the problem. Okay, can't see the problem. Okay, fine, no problem. Let me just give you an example. Consider, for example, that we're in a situation where we need to add multiple, or rather multi-bit binary numbers. Okay, so consider this example. That's I have a binary, or rather a 2-bit binary number, this 11 over here, and I'm adding 1 to it. So in this case, if we're adding the units digits, then I would obtain a result of 10. So the sum is 0, and the carry gets over, or rather gets carried over to the next higher stage for addition. Okay, sorry, excuse me. So in this case, we can see here, if we just look over to the next higher column, in this column we have to add 3 bits. Now that isn't possible by means of a half adder, so we need something which can add up to 3 bits of binary input. So based on that, enter the full adder. Okay, now the full adder is a circuit, or rather another digital circuit of an adder, okay, which is obviously an improvement over the half adder, and the full adder can be obtained by cascading 2 stages of half adders. So if I just consider this square box as half adder 1, okay, there goes the half adder's input bits A and B, and it has its own carry and sum, okay, as usual. All right, and here goes another half adder, okay, that's the half adder 2. So in this example that I showed you here, the 1 bit gets carried over from the previous stage of addition to the next higher stage. So let this type of carries be represented by the term Cin, which is also known as the carry in into the next higher stage from the previous stages of addition of binary numbers. So the carry in forms one of the inputs to half adder 2, and the sum produced in half adder 1 is another input of half adder 2. So the half adder 2, like half adder 1, produces another sum denoted by S dash and a carry, okay, denoted by C2. Okay, the half adder 1 produces a carry of C1. So now both the carries of the half adders are put together into an OR gate, and the resultant that we obtain over here, that's termed as the C out or the carry out, represents the net carry of this full adder stage. So in this case, if we just try and draw our truth table, okay, it would look something like this. Okay, let's just put the data over here, A, B, and the C in, that's a carry in, and at the output stage we have our carry out, all right, and our sum, that's S dash. So for certain types of input combinations in which all the bits are zeros, the sum and carry both are 0. For certain input combinations where one of the bits, any one of the bits is just 1, okay, so for those cases, for this one as well as certain other cases like this also, the sum and carry, the sum comes to 1 while the carry bits are 0, as there is no carry at all. But in cases of certain situations, rather certain combinations where the input bits are such that two of them, or rather, let's say, two bits are ones, okay, and the third bit is a 0. For those cases, the sum is obviously 10, and here the sum bit is a 0 and the carry bit is a 1, okay. And now lastly, by going through all such combinations, we reach to the final combination, which is the case where all the input bits are ones together. So in this case, the result is the result of just the addition of all the three bits over here. We obtain 11, where the sum bit, that's S dash, is also 1, as well as the carry out bit is also 1. So that's how the truth table of a full adder circuit is obtained. So it was just not possible for me to go through all the combinations due to the limitation of time. But if you just carefully go through the combinations and just try and add the various combinations, you would reach the results for the cases that I've shown you over here. Okay, so based on the pattern of outputs obtained in the truth table of the full adder, the circuit of the full adder can be designed by using or rather just cascading two half adder stages in the pretty much similar way. Okay, so here we have our first half adder constructed by using an XOR gate producing the sum of the first of the first half adder. Okay, and here is the carry bit produced from the half adder as well. So there goes our carry. Okay, so this is our first half adder, okay, with input bits A and B, and here's our carry in bit feeding straight into the XOR gate of the next half adder 2. So this is our half adder 1, and here the sum, okay, the sum bit of half adder 1 forms the input, the second input to the XOR gate of half adder 2. Okay, and here goes the AND gate that produces the carry. Okay, let me just draw it in the upper side. That would be quite easier for you all to follow. Okay, so there goes the carry of the second half adder stage. So here's C2 and this is C1 in this case, and here is the S dash, that's the total sum of this half adder, the full adder stage, and both the carries of the two stages are just put in through an OR gate, and this is where we obtain our carry out. Okay, so this is basically the circuit, okay, the practical circuit of a full adder. All right, and based on this, today we have several types of ICs that contain full adder. Okay, like for example, the 7483 is a 4-bit binary adder. Okay, it's a 4-bit binary adder IC that contains 4 full adders inside it. Okay, so basically this IC can be used, is presently used in various types of applications where full adders are required. In bigger systems, we cannot use logic gates to construct the full adder circuits, as they would just take up too much of space. So having said that, we come to the conclusion of our tutorial that adders are the essential parts of electronic data processing. Okay, and keeping that in mind, don't forget to follow our next tutorial on digital electronics, and till then it's goodbye for now, and thank you.